Welcome to our class on section 5.4, logarithmic scales. The required form was due last class. There's also a response of yours that's due, I think it's by class 10, so take a look at the details on the Moodle required form section and read through your responsibilities and then follow the directions. Hopefully right now you're working on project 3. You can see it's due in a few days. What's coming up next class is a quiz on classes 7, 8, 9. That's that material right there, including what we're about to do today on logarithmic scales. Okay, logarithmic scales are used to plot information that varies over a wide scale. For example, here are the populations of some countries and territories in the Americas. Plot these populations on the number line below. The equal spaces between consecutive dots represents 10 million. Okay, so we've got the numbers here. These are all millions. Equal spaces between the dots is all 10 million. And then we've got the populations over here. So you're going to plot, we'll do the first one together. But the US's population when this chart was created was 301 million and change. So let's go ahead and plot 301 million just to the right, basically on that 300 dot. But we'll just plot right over here. And we'll say this is the US right here. So go ahead and pause the video, plot a dot for each of the remaining countries, and then come back when you're done. Okay, so I've plotted the first few here. We've got Brazil, and then Mexico, Canada, Guatemala, and then things get kind of scrunched up. So I've plotted Haiti there, about 8.7 million. And then we get to Suriname, which is under 500,000, but 470,000 people is a lot of people. But in terms of plotting it on this graph, well, we're in trouble because that first dot, it's kind of hard to see, but I tried to plot a dot right here at 1 million. That's this dot right here. So you got your 0 dot, and then right next to it, basically almost on top of it, is a dot for 1 million, and Suriname is between those two dots. So I hardly have any space to put Suriname, but Suriname is not the only country in there. We've also got Barbados, Anguilla, and the Falkland Islands all inside of that space. And the Falkland Islands at 3,000, I mean, it's like compared to the population of the US at 300 plus million, 3,000 is hardly anything. So it's really hard to plot these populations on this scale, this linear scale, because the populations vary so significantly, 300 million down to 3,000. How many orders of magnitude is that? By what power of 10 do we need to multiply 3,000 to bring it up to 300 million? Let's see, 3,000 is here, by 10, by 100, by 1,000, by 10,000, by 100,000. So we're differing by 100,000 fold. That's the number of orders of magnitude that we differ by roughly. And we just can't see that. We can't see that on this scale. So let's come down here to 2. We see that it's difficult to keep things to scale when the data varies so much, in this case from 3,000 to 300 million. What we'd like to do now is find the log of each of the populations and put these numbers in the empty column. So calculators out, we'll do the first one together and then you can pause the video. So we're doing common log of each of these numbers, 301,139,947. About 8.48, just to the nearest hundredth is fine. Actually, probably tenth is even okay. So we'll say about 8.5. So pause the video here, fill in the rest of this table, and then come back when you're done. Okay, so I've filled in my table. I think I've got the right numbers up here. And then we can move on to number 3. It says plot the logs of the populations on this logarithmic scale below. So here are the numbers 0 to 10, and everything we have is between 0 and 10, from 3.5 up to 8.5. So let's plot the US at 8.5 on this scale right here. So the US is now here at 8.5. Pause the video and plot all of the countries here on this scale. Come back when you're ready. Okay, so I've plotted all of my populations here on our logarithmic scale. And in this case, we had no problem at all plotting all of these countries and seeing the spaces in between them. We've got the US at the far right at 300 million, the Falklands at the far left at 3,000. but we can see them both perfectly clearly. In fact, we could plot things a lot bigger than the US and still stay on this scale that gets up to 10, and we could plot things a lot smaller than the Falklands. Okay, number 4a. Let's put the powers of 10 below the corresponding numbers on our log scale. All right, so I don't know if they'll all go below, but the US is out here because the US's population is, let's see, so this is 10 to the 9, and this is 10 to the 8, and the US's population is in between those, right? 10 to the 9 is a billion, 10 to the 8 is 100 million, and the US population is between at 300 million. So we can just work our way all the way down, 10 to the 7, 10 to the 6, 10 to the 5, 10 to the 4, and Gia is just over 10,000. I can see that by looking at this picture, because 10 to the 4 is 10,000, and Anguilla is just to the right, 13,677. So that seems reasonable. The Falklands here are between 1,000 and 10,000. We saw that. 10 squared is 100, 10 to the first, and then 10 to the 0 over here. And then at the far right, 10 to the 10. Okay, so could we fit every country in the world on this scale? Let's see, 10 to the 9, we said that's a billion. So there are countries whose population is right around a billion. I can name 2 of them at this moment. 10 to the 10th is 10 billion. No country is up near 10 billion. In fact, 10 billion is bigger than the whole world. So if we wanted to, we could find the log of the population of the whole planet and put Earth right here. And we could also plot in part B here, it says, can we plot the log of the population of this room on the scale? Okay, so you might not actually be in a room with, well, if you're watching this video, you are hopefully not in a classroom with other students, but if you were, maybe the average class size here is around 20 students. So could we plot on this scale 20 students? Well, let's see, if there's 20 students, we take the log of 20, we'll type that into our calculator. Log of 20 is about 1.3. 1.3 we can put on this scale, no problem. Right around here. This is a class of 20 students. So can you imagine here a scale where there's enough flexibility that we can see very clearly both a class of 20 students right there at that dot on the far left and the population of the entire Earth, this dot on the far right. Plenty of space in between so we can make things out. So log scales are really good for displaying information that varies wildly in terms of number of order of, in terms of the order of magnitude difference. From 3 million down to 3,000 down to 20, no problem on a log scale. Real problem on a linear scale. Couldn't see anything here on the far left. Okay, number 5 says estimate the population of Argentina. Okay, so this is kind of going the other direction. Argentina was given as one of these dots here. The Argentina dot is this one. So first thing we need to do is ballpark that number. I don't know, 7.6. And that's supposed to be the log of the population. So if that's the log of the population, then the population must be 10 to that number, 10 to the 7.6. So we can type that on the calculator. We can type it wrong on the calculator. So population of Argentina, let's count very carefully, about 39.8 million. So it's easy to put things on the scale, to go from the true population to the scaled population, and it's easy to go the other way, to take the scaled population and find the true population. Number 6, when using a logarithmic scale, each step to the right equates to a blank increase in the actual value. So going from this dot to this dot, no, I did not do this right. I'm glad I picked those 2 dots. This should have been 10 to the 6th. Okay, so going from this dot to this dot means going from a true population of 10 to the 5th to a population of 10 to the 6th. That's a 10-fold increase in the actual value. Thus, an earthquake of magnitude 5 is blank times more powerful than an earthquake of magnitude 3. So earthquakes fall on this logarithmic scale. It's called the Richter scale. So an earthquake of magnitude 5 is blank times more powerful than an earthquake of magnitude 3. Well, every step to the right is 10 times as powerful. So if we are going from 5 on the Richter scale down to a 4, that's 10 times as powerful. But 4 to 3 is another 10 times as powerful. So the net result here is 10 times 10, or 100 times more powerful. So every little change in the Richter scale is a very big change in reality. The Richter scale is one of these things where there's a log that's been applied to the intensity of the tremors of the earthquake. So it can be kind of misleading if you're not aware that there's logs involved. A rock concert at 110 decibels is blank times more intense than a conversation at 50 decibels. So it seems like we can play the same game, except there's one little twist here. If you recall that the decibel rating, number of decibels, was 10 times the log of some stuff. So if we want to do this business about just saying that every step to the right is a 10-fold increase, what we need to do is get rid of this 10 that's sitting in the front of the decibel rating. So if I had a decibel rating of, 110, that's equal to 10 times the log of something. If we divide both sides by this 10, then we get 11 is equal to the log of the 1. And doing the same thing over here, it was 50. It's 10 times the log of some stuff. And so divide by 10, we get 5 is equal to the log of the actual stuff. So now I can understand here about this walking along. I'm walking from an 11 to a 5. And every single step that I take is a 10-fold increase. So how many steps between 11 and 5? There are 6 steps. So 10 times 10 times 10, 6 of them. 10 to the 6th, or a million. Rock concert is a million times more intense than a conversation at 50 decibels. Okay, let's have a look at this Excel file right here, class number 9, in events in biological history. Okay, so here it is, and I'll just point out at this stage that this document was created by Niels Abel, A-H-B-E-L. You should check out his website at abel.com, A-H-B-E-L.com. That link is up on our Moodle page. In fact, if you go into the materials for class number 9, this class, you will find this Excel spreadsheet, so you can play around with it and maybe check out his site as well. Okay, so here's what's going on. We've got some very important events in our history, biological history. So we've got prokaryotic cell organisms developing about 3 billion years ago, and you can see that here in blue, same color as this blue back here. So 3 billion years ago is what happened. Nothing in this list happened between, in the 500 million years that passed. Keep going, keep going. Eventually we get here to about 1.5 billion years ago when the eukaryotic cell organisms develop. Not a whole lot happening until 500,000 years ago with the rise of the fish first vertebrates. The fish were the first vertebrates, and that's in green, color-coded here. So here's the deal. There's a lot of action happening in a relatively short period of time, right? We've got mammals, we've got monkeys, chimpanzee, and the hominid lines, Homo erectus, existing, taming fire, Homo sapiens, using fire to cast copper, and then writing in Sumeria. A lot of action happening in a very short period of time. In fact, the last dot that I can see here, well, let's see. There's this blue one. That blue one right there, I think, is this one here at 1 million. Does that make sense? Let's go with that. So I think that blue one is 1 million, but then I don't see the green one at all. This 500,000 I can't even see because it's in here in this mess. There's this yellow thing, Homo sapiens existing 50,000 years ago. I can't see it. Homo sapiens casting fire. I don't see that color either. I do see this one right here, the red, I think is that, but I think it's only there because it's the last one in the list. So just like the populations of the countries we talked about having so much happening in a short space, same kind of thing here. Very long period of time. 6,000 years is a drop in the bucket compared to 3 billion years, so we can't see all the action happening in the recent history because this 300 billion is just dragging everything out. So here's a linear scale. But if we wanted to, we could take logs of all these numbers and tame them, bring them back to something that we can see. So I'm going to click this button here, logarithmic scale. And here we are, logarithmic scale. Notice that every step to the right now is a 10-fold increase, just like we saw before. All right, great. 6,000 years ago, the log of 6,000 apparently is in here someplace. And we can see that. And then now I can finally see this purple. I didn't see the casting fire to using fire to cast copper before. Yellow making its first appearance 50,000 years ago. And at the far right, we can see over here, that blue one is this blue one up here. So we can see all of these important events, no problem. We needed to use a log scale to space these things out so we could see them all, but we just have to recognize every step to the right is now a 10-fold increase. You don't increase by 1 anymore or by 500,000 years every time. You multiply by 10. So there's a good use of log scales so that we can see what's going on. Another place where we can see log scales is stock prices. So we're going to look up Apple's stock price at this website right here. So I've typed in the website. I click right over here to this lookup button, and we'll just type in Apple. And today, Apple stock closed at $497.91 per share. That was down 59 cents, which is a loss of only about 0.12%. And you can see the ups and the downs in the price of Apple stock today. This is just 10 a.m. or 9 a.m. I guess until 4 p.m., which is when the market's closed. But I'm not interested in just the meanderings of the stock price today. I want to look at the Apple stock price over its entire history, which is about 30 years. I'll go all the way back here to pre-1985. Looks like September of 84 is when maybe Apple stock first publicly traded. You can see it right up there. And so if we look at this this graph, we would say that Apple stock did pretty much nothing. I mean, it looks like it rose a little bit, but really inconsequential things, a little blip there, but then eventually we're kind of back down here. And really nothing's happening with Apple stock until about, I don't know, 2004. And from 1985 to 2004, that's almost 20 years, 20 years of nothing. And then you can see in the last, in the last 10 years or so, tremendous growth, lots of oscillations, highs and lows. It reached a peak back here, right there at the top. You can see if you look at the top left of this screen, maybe I can get over there. Right below my mouse, you can see that the price up there near the peak was $667 a share. Right now it's at about $500 a share. That was back in September of 2012. Okay, so really, did the Apple stock do nothing for 20 years? The answer is no. It actually did something. Let's come back here to the beginning. September of 84, Apple stock looks like it's starting to trade publicly at about $3.48. And then we're going to come over to here, right there. And again, if we take a look up here, we can see Apple stock trading at $14.63. So it went from $3.50 to $14.63. So that's more than 4-fold increase. Whatever money you put into Apple in 1984, looks like just 3 years later, it became 4 times as much. That's huge. That's what a great return, 4 times as big. But it looks like nothing. It looks like nothing happened. Why did it look like nothing happened? Because compared to the current stock price of $500, this $3.50 and this $14 are pretty much the same thing. And they're both pretty much nothing relative to the tremendous stock prices that we're at now and in recent history, the last 10 years. Okay, so what's a good way to see this? Well, what if we start taking logs of these stock prices? Log of $500, log of $3, and plotting those instead. So here you can see the linear scale. Every time you take a step up, you are going up by 0.1 thousand. That's kind of a funny unit of measure. It's $100, right? 1/10 of 1,000. $100, $200, $300, $400, $500 is right where we are now. $600, the peak was up there at 6 and change. So every step up is $100 increase. Let's change something. We're going to go into chart settings, and we're going to go to line type. No, we're not. We're going to go to scale, and instead of log linear, we're going to choose log. And all of a sudden, we can see everything. This still goes back to 1984. In 1984, the price still opened here at $3.48, but now I can actually see the tremendous growth. going up to our peak of, I think we found something around $14 right there. And you can see how much higher that is than it was before. It more than quadrupled in value. And then fairly steady, some ups and downs, but then we start to see some more ups. And the idea is that we can see $600 on the same scale as we can see $3.50 because we've logged everything. Now notice that equal steps up here actually still, they now correspond to tenfold increases. So to go from 0 to 10 and then 10 to 20, you can see the space in between here. So if you want equal dollar changes, you got to really shrink the spaces down. But still, every step up is a tenfold increase. But they've put the scales here, so the numbers here, so that we can actually see the prices still. Okay, so stock prices, you can see a lot more of the variations if you use a log scale. Number 8, log scales and regression. Suppose we have a set of data for a model with two variables and believe that there is an exponential relationship between the variables. Thus, we seek an equation of the form y equals a times b to the x that best fits our data. So we've seen a times b to the x or a times b to the t. That's our standard for exponential growth. The calculator can do this for us directly, but if we want to get a sense of whether an exponential model is reasonable before we use the calculator, we're going to take the log of both sides and then use some of those nice properties of logs. So suppose that you have some data and that it happens that y equals a times b to the x is a good fit, but we don't know that yet. But let's just pretend we have the equation and we're going to take the log of both sides. So we go log of y equals log of a times b to the x. And now we're going to start using some of those properties. So first, this is a product. Products become sums. And then we've got a power. That power can come in the front. So we go log a plus x log b. And then this was equal to log y. Okay, so let's get a sense of what's happening here. We are now going to make a new graph, and the graph is going to be x versus log y. So x is normal, but the new y-axis is actually log y. So I'm going to say that this thing right here is like y equals, okay, now a and b were just numbers, and so the log of a number is just a number, plus. Down here, this guy x, well, it's ordinary x. Nothing has changed there. X is still on the horizontal. And b is a number, so that means that log of b is also a number. So ultimately what we're plotting here is, let's put this up here, y equals some number plus x times a number. And if I put that in a different context, y equals b plus x times m. Some number plus x times some other number. And what's the graph of that equation? It's a line. So if we were to plot our points on this set of axes, and if in fact it actually were an exponential model to start with, then we would see some nice linear relationship or close to it. So this would be a great way to decide without any technology whether or not an exponential model might be appropriate, is you just take the log of both sides and then plot the original x's versus the logged y values. We'll see that specifically down below. Number 9. Now let's suppose we have data that follow a power relationship, a times x to the b. Notice the variable is no longer in the exponent, it's down below. Again, we're going to hit both sides with the log. And we're going to use some of our nice properties of logs here. Product becomes sum. Power comes down in the front. This was log y on the left-hand side. And now it says we're going to plot log x versus log y. So in this case, both of the variables will be logged. So this will be log x. This is log y. So I'm going to kind of redefine. This guy right here is really behaving like y. This guy is really my x. The other guys are just numbers, right? Log a is just a number, plus b is just a number. So again, I'm looking at y equals a number plus a number times x. and that's a linear relationship. So if we had some power data, not exponential, but power, then plotting the log of the x values with the log of the corresponding y values will give you a nice line. That's a really easy way to figure out if your data might be exponential or power or neither. Okay, so here's the summary. If you have x is really x, but y becomes log y, then exponential models become linear. This is called semi-log. If you just Google semi-log graph paper, you can print it out. You'll see linear scales on the one, but then the changing scales where, just like on the stock market price, we saw big space and then smaller, smaller, smaller. So log on the one. And then over here, if you do log x and log y, then power models become linear. And this is called log-log paper instead of semi-log paper. This is log-log paper. You can Google that and print out a piece or two if you want to play around. Let's actually do some numbers here. Number 10. Let's fill in the blanks of the following table to the nearest tenth and then calculate some slopes. Next, we'll decide if an exponential or power model is appropriate, and we'll find the equation of a line. Then we'll find the equation that models the data. Finally, we'll check the equation we found against the equation the calculator gives us in 2 seconds using regression, thereby defeating the purpose of all our hard work. I'm nothing if not honest with you folks. So let's start crunching some numbers here. So we want to do logs of the x's and we want to do logs of the y's. So let's start here. Okay, so we're going to do log of 1.9 and log of 3.2, log 5.1, and then log of 8.9. Okay, so I'm going to copy those numbers. I think we said nearest tenth is okay. So we're just going to write all these numbers into that first column. So 0.3, 5, 7, and 9. Okay, and then same thing for the log of y. But you know, I'm kind of tired of typing all that stuff. So there is a shortcut here. Why don't we just start doing the shortcut? We're going to start entering this information into our lists. So for some of you, this will look familiar, and if not, that's okay. I'm not going to test you on this, but it's nice to know some of the functionality of your calculator. So hit the Stat button, and then hit Enter on the very first option. And then we're just going to type in, so let me clear my list. So the way to clear a list is not hit Delete, but it's hit Clear and then Enter from up at the top. Okay, if your lists don't look like L1 and L2, just go down here. So from the home screen, do stat and then number 5, and then enter. And I think that should clear, or that should restore the list names, the standard list names. Okay, so we got L1, L2, L3, L4. So we're just going to start typing in here 1.9 and then enter. And then we'll type in all the data. And then over on the next column, we'll just do the y values. So I have the advantage of being able to use a number pad here. So pause the video and come back when you're ready. Okay, so I guess the whole idea maybe first is to think about whether or not this might be exponential or a power, or it's hard to tell. So how about we go into stat plot? I'd really like to see a plot of these points all plotted, 4 points here. We want to see them plotted. So go into stat plot, second stat plot. We're going to turn plot 1 on, so go into enter. Hit enter there to turn it on. Pause the video if you need. Make sure that all of your settings match mine. You can change your settings by scrolling around. Hitting enter will change to a different option. This is what it should say. And then if we do zoom stat, stat is near the bottom here, it's number 9, then the calculator will find our points. So there are our 4 points. So is it an exponential? Well, it kind of looks like exponential growth. But could it be a power function? Remember, power functions are like a times x to the b, so it could be like x squared or x cubed or x to the 5th. And it's hard for me to tell which it is. It kind of looks like an x squared function, or maybe some variation of x squared. So it's really hard to know whether exponential or power, or maybe neither, is appropriate in this case. So that's why we got to do some work. Okay, so we found logs here, but it turns out the calculator can find those for us as well since we put them into our list. So hit stat and then enter, and scroll over here to this L3 column. What I want to do is tell the calculator to just take the log of L1, but you can't do it here. You got to do it up above, and you also want to do it in quotation marks. So quotes are right there. It's kind of aqua, the color right on the plus sign. So we do alpha and then that thing, and then we type log right there. And then I just wanted to take a log of that first column, which is called L1. L1 is in yellow, right on top of the 1. Second 1. Enter. And just like that, calculator zips through all of the calculations that we did. These are rounded. These are much more accurate than the ones that I wrote down. Okay, so far so good. And then we're going to do the same thing for log y. So go over to L4, up to the top, quotation mark, log, second L2. So these are the log y values. So I'm going to write those in here, 1.2, 1.5, 2.0, and 2.9. Okay, so we've got our data. And the next thing it says is calculate some slopes. All right, so let's think about what slopes we're going to calculate. The first thing we could try is to think about the graph of log y versus just plain old x. So I'm going to circle those two columns here. Log y versus plain old x. And so if our points are of the form x log y, then the first one, for example, is 1.9 and 1.2. And the second one is a 3.2 and a 1.5. And likewise down for the last 2 points. And so if, in fact, we had an exponential model to start with, then the these points right here, the 4 modified points, would form roughly a straight line. And if they form roughly a straight line, then their slopes should be pretty consistent. So what we'd like to do is find the slope of the line connecting these 2 points, and then the slope of the line connecting the next 2 points. Oops, 5.1 with 2.0, and then 8.9 with 2.9. So what we're going to do is calculate slopes here, and here, and here. 3 different slopes. So pause the video, calculate slopes of the line segments connecting those 3 pairs of points. You'll get a little more accuracy if you don't use such rounded ones here. Maybe before you pause the video, let's just add hundredths in there to get a little bit more accuracy. So 4, 4, 7, nope, 4, 4, that should be a 9, 7, and then 8, 5. So this is 4, 4, 1.97, 2.95. I think we got that right. Nope, 2.85 on the last one. Okay, so see if you can use those numbers there and find slopes of 3 different lines that I've written down, and see if these numbers are fairly consistent or if they are if they vary pretty dramatically. Okay, I think that's right. One last check, and then you guys will go to work. Okay, I think we're good. So pause the video here, calculate 3 slopes, and come back. Okay, so here are the slopes I got, and they are all pretty darn close to each other. I think they'd be a little closer if we had used a few more digits in the log y column. But this is pretty compelling that those 4 points, the modified points, these ones here, lie on approximately a straight line. Slopes are very near each other. So what does that mean? Well, it means that the original data was probably pretty darn close to exponential because it became linear when we used this x and log y scale. Okay, just for kicks, we can also try the other one, which is the log x log y scale. That's here. So log x log y, For example, let's see, so I can circle here in green. That's in this column and the column we've already used here. So points here are something like 0.3 and 1.24, and 0.5 and 1.54, 0.7, 1.97, and then 0.9, 2.85. And so just like before, we're going to want to find three slopes and see if they're anything near each other or if they vary pretty dramatically. So pause the video and come back when you're done. Okay, so I've got my slopes here, 1.5, 2.15, 4.4. Those slopes vary quite dramatically. So if I were to plot these 4 points, I wouldn't get anything anywhere near a line. I'd have a point here and a point here and a point here. It didn't, taking logs of both of them didn't straighten out the curve. Still curvy. So a power model is not appropriate in this case. So I think we're ready to actually get the equation of the exponential model that fits best here. So going back up to the work that we did before, well, actually, let's find the equation of this line that has a slope of roughly 0.23 and then hits any of these points right here. Doesn't matter which one we pick. So let's find that line, find the equation of that line, I should say. Okay, so we're going to use y equals mx plus b to find the equation of a line that hits these points. So we know the slope is roughly, we'll say 0.23. And then we can just pick any point that we want from that list. I'll pick the first one, 1.9. Nope. The y value of the first one is 1.24. And then 1.9 is here. And then plus b. And so to find b, all we need to do is 1.24 and then subtract 0.23 times 1.9. So we can do that over here. I guess I would like to get maybe a slightly more accurate number than this 1.24. It's easy enough to do on the calculator. So here we go. 1.24, where did it come from? It came from the log of this guy. So we'll start there. Log of 17.3. And then we subtract 0.23, which was our estimate for the slope, times 1.9, which was the exact number given to us. So we get about 0.8. Okay, so that means that the equation of our line is then y equals 0.23, that's our estimate for the slope, looking at the blue numbers, x plus 0.8. Okay, so far so good. And then we can bring it back together. So which is our exponential one? It's not here, it's up above. Okay, so here in blue towards the top, we found that the equation of the line that we got, this y equals a number plus x times a number, was really log of y equals log of a plus x log of b. Okay, so I'm going to write that equation down at the bottom. And this equation is supposed to match up with our equation that we had there in black. I'll just write it here. So that means the y is the 0.23x. It's kind of funny, but I'll write it in that order. And then plus 0.8. So x is x, no problem. The log y, remember, is what we're calling y. That's no problem. But look, we get information here. Log of a must be 0.8. And log of b must be 0.23. And so we can find a and b, and then I think we're done. So let's just hit both sides with a 10 here. So follow the football pattern. 10 to the 0.8 is a. So 10 raised to the 0.8. And then 10 raised to the 0.23 is b. Okay, so there's our a and our b, 6.3 and 1.7. Okay, so last piece of this puzzle, our original formula was y equals a times b to the x. exponential turned out to be appropriate here because the log of y versus x became very close to linear. So the a is 6.3, the b is 1.7 raised to the x. So let's go ahead and go back in here on the calculator. I'm going to call this guy b, just using the store command here. And then we can do second entry a couple of times to get back to our a, and we'll call that a. And then if we go back here, remember we've got this plot. Turns out it's going to be pretty close to an exponential graph, but what's the equation of that graph? It's right here. It's what we did all this work for. Y equals 6.3, but let's call it a because that's the accurate answer, times 1.7, that was our b, we'll call it b, raised to the, whoops, alpha b raised to the x. So if we've done this right, then that graph should be pretty darn close to going through these points. Ooh. All right. So we just found an exponential model that comes very, very close to the points that were given. And we did it really without any super technology. We had to do logs, but we could look, there were like paper tables of log values. We could have looked these up without any calculators. And then we didn't do any arithmetic that was too hard. And then over here, we did 10 to the 0.8, but that's also something we could have looked up on a table. So really without much technology, if any, we were able to come up with an exponential equation that's the best fit for that data, which is pretty darn cool. Okay, so that's the good news. The bad news is that the calculator can do this and make us feel like we're just spinning our wheels there because the calculator is so powerful. If you go to the home screen and hit clear, then hit the stat button, go over to calc, and we're looking for exponential regression. And if you just hit enter, the default is going to be that it's it's taking the values in L1 and L2, which is exactly what I want. So let's hit enter. And it says that the formula is a times b to the x. That's the same formula we had. And it says the a is 6.3. That sounds familiar. And the b is 1.7. That sounds familiar. R squared value is quite close to 1. That's super. So we were able to do all that without really relying on any of this crazy technology available to us, which is pretty neat. Okay, 11. We won't be doing much with regression this semester, but there is a reference sheet called Fitting Curves to Data. You'll find it in Moodle that walks you through how to do all this regression stuff on your calculator. We did it here, but you can check out the description on Moodle as well if you wish. Okay, learning objectives are in the usual place, and that is that.